today I discuss about digital reaction. These are the points which we will discuss in this lecture. On general introduction to reactivity of dienes and dienophiles, residual selectivity of the Diels Alder reaction, and stoichiometry of the Diels Alder reaction. I discuss about general introduction. Diels Alder reaction is the pericyclic reaction. It is 4 plus 2 cyclic addition reaction between conjugated diene and dienophile under thermal condition to produce six member cyclic adduct. The instead of diene, alpha beta unsaturated aldehyde, alpha beta unsaturated ketone, and alpha beta unsaturated amine, and the instead of dienophile, alkyne, nitrile, nitroso, aldehyde, ketone, amine, and azo compound, etc. If the Diels Alder reaction leads to the formation of heterocyclic adduct, then it is called hetero-Diels Alder reaction. And reaction of butadiene with alkyne to gives cyclohexadiene derivative. Now I discuss our reactivity of dienes and dienophile. In Diels Alder reaction under normal electronic demand, homo of diene combines the HOMO of dienophile to forms Diels Alder adduct. There are two component in Diels Alder reaction, diene and dienable. So the rate is affected by the nature of diene and dienophile. Let's first discuss the reactivity of diene. The reactivity of diene increases by the following factors. One is ability of the diene to adopt an H6 conformation, planarity of the system, electron donor groups. Let's take example of 1,3-butadiene. This is S trans and this is S6. S trans is more stable than S6 because of less steric hindrance. S6 undergoes Diels Alder reaction while S trans does not. So any factor that favors S6 conformation increase the reactivity of diene towards Diels Alder reaction, while any factor that favors S trans decrease the reactivity of diene towards Diels Alder reaction. So the dienes with the in4 H6 conformation have exceptionally high reactivity. For example, reactivity of 1, 2, 3 is higher towards Diels Alder reaction with maleic anhydride than 4, 5, 6 because in 1, 2, 3 diene is locked in the H6 conformation and the compound H is more reactivity than compound 8 because the compound 8 H6 conformation is less favored due to the steric hindrance, and the compound 9 and 5 have higher reactivity than compound 6 due to the presence of electron donor group. Compound 9 is more reactivity than compound 5 because in compound 9, due to the bulky T-butyl group, S trans is not favored and S6 is more favored. Now discuss the reactivity of dienophile in Diels Alder reaction. Factor inducing reactivity of dienophiles: electron withdrawing group, a weak pi bond, release of ring strain. This series of compound showing relative reactivity of different compound with respect to acrylonitrile. Here we can see that more electron deficiency the dienophile, higher is the reactivity. Now ratio selectivity of Dusalted reaction. The ratio selectivity of the Dusalted reaction of unsymmetrical diene with unsymmetrical dienophiles can be predicted by the orthopara rule. One substituted dienes and monosubstituted diene react to give orthoadac as the major product. Two substituted dienes and monosubstituted dienophile react to give paradag as the major product. If you have one substituted diene and monosubstituted dienophile, here are two possible ratio isomeric product. Orientation of diene and dienophile like this will give orthoadact, while orientation of diene and dienophile like this give meta-attack. According to the orthopara rules, ortho-attack will be major while meta-attack will be minor. Similarly, two substituted diene and monosubstituted dienophile can orient like this to form para-attack, or they can orientation like this to give meta-attack. According to the orthopara rule, para-attack will be major product while meta-attack will be the minor. These rules is true for almost every conformation of electron withdrawing and electron donating groups, except one case where X and Y both are electron donors. In this case, there is marginary meta selectivity. For more clarification, let's have some example for the clarification of first point. This substitution X and Y along with the percentage product distribution having shown in this table, where we can see that if respected the nature of X and Y, when they are electron donating and electron withdrawing, orthoaddict have been found with the major product. In the case of 3, 4, 5, there was only orthoaddict, could not be from meta-addict. For clarification of the second point, let's have another table. In this case, we can see that if respect of the nature of substituent, para-addict is the major addict. In some case, like example 13 and 14, formation of meta-addict could not be even detected. Now discuss about stoichiometry of the Diels-Alder reaction. The Diels-Alder reaction is stoichiospecific. If there is stoichiometry in the dienophile, then it is faithfully reproduced in the product. Thus, cis and trans dienophiles give different diastereoisomers of the product. Ester of malic acid and formic acid provide a simple example. In both cases, the ester groups simply state they are cis in the dienophile. In the first reaction, remain cis in the Diels Alder product. They are trans in the dienophile in the second reaction and remain trans in the Diels Alder product.